Hugh Dyer, a director in RSK's Geosciences business. Welcome to the October edition of our 2025 series of Down to Earth webinars. These will cover a broad range of subjects and are available afterwards on our YouTube channel alongside previous talks. Our talk today will be given by Dr Anil Waduge, an Associate Director in our Contaminated Land team. Anil will outline the challenges and options for remediation of groundwater. But firstly, a brief note on the housekeeping during the talk. All attendees' microphones are automatically muted throughout the webinar. During the presentation, you can post questions online and there'll be a Q&A session at the end of the presentation. We'll answer as many questions as possible at the end of the talk. Those that can't be answered due to time constraints will be answered after the webinar. Shortly after the webinar, you will receive a link to a short survey. If you can take a few minutes to provide feedback, please, so we can improve on future webinars. Now, please let me introduce our speaker today. Dr. Anil has over 20 years experience in contaminated land management, gained through consultancy, contracting, and as a regulator as part of the Groundwater and Contaminated Land team at the Environment Agency. He's a chartered scientist and holds a PhD from Cambridge University. Anil has worked across a wide range of sectors and on projects throughout the UK, Europe, and the Middle East. He's a long-standing member of the SOBRA NAPL group and is currently developing guidance on NAPL remediation for UK practitioners. I'll now hand over to Anil to provide an overview of the challenges, groundwater investigation and remediation. So we'll turn off our cameras and Anil can start the presentation.
Okay, thank you, Hugh. Good afternoon, everybody. Welcome to today's webinar on introduction to groundwater remediation. Please note that I will not go deep into technical matters. I will try my best to give a simple kind of non-technical presentation as much as possible. Hopefully, at the end of this presentation, you will have a better understanding of groundwater remediation process and then how and what what you should do to meet your remediation objectives effectively and economically at your site. So this is the agenda. First, I will very briefly tell you what is groundwater and then the importance of the groundwater. Then very briefly introduce you the risk management process and the remediation decision-making process. Then I will outline some of the common groundwater remediation technologies, and then finally I will present a case study to finish this presentations. What is groundwater? So simply, groundwater is the water found beneath the Earth's surface. The legal definition of the groundwater, according to gov.uk, is all water which is below the surface of the ground in the saturation zone and in the direct contact with the ground or subsoil. So where does it come from? The groundwater forms naturally as a part of the water cycle, now as shown in this figure. When it rains or snows, some of that water soaks into the ground, moving down through the soil and rock layers to reach at the groundwater. The importance, the groundwater is essential for our water supply and the environment. It provides about 30% of the public water supply in England and Wales, and maybe it could be even more in regions like Southeast. So it supports agriculture, industrial, and sustained river flows and wetland during dry periods. However, due to slow recovery, the groundwater is vulnerable to over-abstraction and pollution. So careful management is crucial for long-term sustainability. The groundwater pollution, the groundwater becomes contaminated when pollutants enter the subsurface. This can happen through industrial spills or leak from fuel or oil storage, agricultural runoff, landfill leachates, wastewater discharge, abandoned mines, or leak in septic tank or sewers. Therefore, it is necessary to regulate these activities to control the emissions and hence to protect our groundwater. And if the contamination does occur, the groundwater remediation is necessary to protect both people and environment. The regulatory drivers, when it's come to the groundwater remediation, there's a long list of legislations which drive the groundwater remediations. I have just shows a few main regulatory drivers here, but there are more regulations associated with the groundwater remediations. So, in simply the requirement of the EU Water Framework Directives and Groundwater Directives provides the overarching groundwater regulations, which has been transposed into UK law. The land contamination aspects are then addressed within the planning regime and Part 2A requirements. So, as a summary, you may have to manage potential groundwater contamination as part of a planning application for redevelopment, or as a part of as Part 2A obligations, or as a voluntary remediations, as a regulatory requirements such as remediation notice or anti-pollution work notice, or where a decision has been made to deal with the historic contamination identified through environmental permitting site condition reports. The risk management process, when groundwater contamination is identified, it should be managed following the Land Contamination Risk Management LCRM framework, web-based guidance available in the Gov.uk. The LCRM framework provides a structured risk-based approach to managing sites with potential or actual contaminations, and it promotes a clear, auditable process aligned with the sustainable remediation principles, encouraging transparent decision-making, stakeholder engagement, proportionate actions to manage risk effectively. Now, as shown in here in the slide, the LCRM framework is built around three main stages: the risk assessment, option appraisals, and remediation and verifications. So, stage one in risk assessment, that's we will sort of like do the desk study and the site investigation to estimate and evaluate the risk. And if we identify the unacceptable risk, then the site goes to the stage two, option appraisals. And there we will screen the feasible remediation options and do the detailed evaluation to select remediation options for our sites. And then in stage three, we develop or design the remediation stage, remediation strategy, and then do the remediation, and then finally we verify the sites to confirm that remediation objectives have been achieved. So this is very briefly, this is the risk management process, and you may have to follow it from the beginning to the end if you are going to remediate the groundwater beneath the site. In general, this is the approach. However, as you know, if there's like a new contamination, new pollution, the approach may be slightly different, and slightly different. And you probably have to address, contain your problem first, and then address the source first, and then sort of deal with the subsequent contamination issues later. Conceptual site model. Before starting the groundwater remediation, it is essential to develop an appropriate conceptual site model, as always we do. The LCRM defined the CSM, the conceptual site model, as the representation of the characteristic of the site in a diagrammatic or written form that shows the possible relationships between contaminant sources, pathways, and receptors. A series of investigation, such as borehole trial pits, a collection of soil and groundwater for laboratory testing, maybe geophysics, leaf investigation, NAPL mobility assessment, etc. Sort of like a series of investigation in different phases. Different phases will be required to understand the problem, and then collect data on geology, hydrogeology, and contaminant distribution to develop an appropriate conceptual site model to determine the complete contaminant linkages, which requires the remediation at the site. So, as you know, the risk assessment is a tiered approach. There are three tiers as shown in this slide in this triangle here. PRA, predominant risk assessment, GQRA, generic quantitative risk assessment, and DQRA, detailed quantitative risk assessment. Probably it is clear to all of you that in general, higher the tier of the risk assessment, the lower the requirement of remediation. So when it's come to the groundwater remediations, in general, it would be better to complete the detailed quantitative risk assessment before starting remediation. Just to quickly remind you, contaminant linkage, as shown bottom of the slide, is the relationship between the source pathways and receptors. All three components of source pathway and receptor need to be interconnected or linked to have a complete contaminant linkage. If they are not connected or not linked, then there's no risk. If there's no risk, we don't have to do the remediation. The site investigation versus remediation cost. The understanding the relationship between the site investigation and the remediation cost is crucial. So I think it may be worth to spend a few minutes to talk about this. Now, this figure here shows conceptually the variation of site investigation and remediation cost with the degree of investigation. As shown here, in general, the higher the degree of investigation, the lower the potential remediation cost, and vice versa. Insufficient site investigation increases unknowns and uncertainties, leading to higher remediation cost. Think the in situ remediation, groundwater remediation, like a blank canvas. If we can't see any, with only a few data points, we are trying to model the site to find the solutions. So it's like building a Lego. We can't have a finished product with a couple of pieces. So we need to continue the site investigation until we have enough data to develop a robust CSM, conceptual site model. Only at this point we can design an appropriate, effective, economical, and sustainable remediation approach for the sites. So, so that's why it is important to carry out a sufficient investigation before doing the groundwater remediation. The remediation decision-making process, stage 2 option appraisals in the LCRM framework. Now, this is the stage we select an appropriate remediation options for a site. So first, you have to screen feasible remediation options, and then complete a detailed evaluation of remediation options to identify technically solid or technically effective remediation options for a site. And then carry out the sustainability assessment for the first 3 or 4 or maybe even 5 remediation options ranked from the or select from the detailed evaluation. The reason to select the first few remediation options to do the sustainability assessment is because we need technically effective remediation options to manage the identified risk appropriately at the site. So by doing that way, we can make sure that the option selected is not only sustainable, but also technically effective to address the identified risk at the sites. So detailed evaluation in general is a multi-criteria analysis. You have to consider criteria listed in the LCRM stage 2. Now, figure in the left side corner shows the criteria we have to consider, such as regulatory stakeholder health and safety requirements, durability, cost, track record, effectiveness, and so on. So basically, all the remediation options should be assessed against these criteria in order to determine the most technically effective remediation option for our sites. And then the sustainability assessment should be carried out in line with the guidance given in the SURF UK. So when it's come to the sustainable remediation, one important thing to remember is that the sustainability cannot override or compromise your risk. So if you have a risk at your site, you do have to do the risk mitigation work to manage your identified risk appropriately at the site. Now, sadly, it seems sometimes that some people misuse or misinterpret the sustainability, and they are trying to use the sustainability as a jail-free card, not to do appropriate risk mitigation work at their site. So it's a little bit sad to see. However, sustainability is not for that. The whole idea or the concept of the sustainable remediation is to remediate or manage your unacceptable risk in a sustainable manner, considering environmental, economic, and social aspect of your project. In situ groundwater remediation. The groundwater remediation is one of the most difficult environmental challenges. So achieving doing the remediation effectively or achieving remediation objective is not a chance, luck, or definitely not a magic. So cleaning water that we cannot see, trapped within a complex heterogeneous soil or rock in a deep underground, hard to reach, difficult to control, with lots of unknown and uncertainties. So all of this making it's a very complex problem, and also it's make remediation technically demanding, challenging, and long-term requirements. So to address these challenges, we need a systematic data-driven approach with a thoughtful process to meet remediation objectives. Now, when we are doing the remediation, in addition to these challenges, there's a different issue. In my view, the remediation discipline is not very well regulated in the UK. No firm standards. Also, I mean, our regulators are probably not technically strong enough. There are, well, don't misunderstood, but there are lots of regulators who are technically very strong. However, not many. We need lots of them. Because of that, I think the people become remediation specialists within a day. Perhaps they have no clue what they are doing or what they are talking. Just digging some soil or pumping some water is not remediation. And then they will try to sign off the site saying that no further work are required due to a sustainability or cost-benefit analysis. Now, this is a little bit crazy, and this is not remediation, and we need a little bit more than that. The success of groundwater remediation. The success of groundwater remediation depends on more than just applying technology at a site. It requires critical thinking at every stage to understand the site complexities and associated risk, and to make the correct decision during the process when you have the data. The remediation should be a data-driven approach grounded in sound science and physics to ensure that decisions are based on site-specific facts and evidence rather than the assumptions. And then, if possible, avoid vendor-driven design. The solution should be tailored to site-specific conditions rather than product availability. So it would be better to assess the whole spectrum of remediation option available rather than limiting to a vendor's capability. And then the adaptive designs, very important. To keep the project flexible, allowing adjustment as new information emerges. As I said before, when remediating groundwater, you are dealing with lots of unknowns. So during the groundwater remediation, expect the unexpectations and don't be surprised with that. So therefore, our design should allow to make the real-time adjustment in response to remediation process performance. So that's why we need the adaptive design. And then the quality management. It's also important, strong quality management, safeguard consistency, accountability, and reliability of your remediations, which is vital for successful remediations. Also, quality management will help detection, diagnosis, correction, and prevention troubleshooting during remediations. And then finally, competency. So it is very, very important. Find a competent consultant or contractor, because their knowledge, skill, experience, their data interpretation and extrapolation and decision making will make a big difference to the success of your remediations. So if you blend all these principles together, you can turn your challenging groundwater remediation into a successful outcome without needing luck chance of magic. The groundwater remediation risk profile. A remediation risk profile reflects the balance between how long a project will take and how much it will cost, both of which are often uncertain. The blue circle is our target nominal estimated time and cost. However, due to lots of reasons, including unknowns and lack of site-specific informations and wrong selection of the options and poor designs, like this kind of reasons, the actual time and cost to complete will increase, as shown in this green oval. So that is the potential remediation risk profile or risk envelope that we should expect during our remediation. So longer remediation times can increase exposure to operational, regulatory, and reputational risk, while the higher or escalating costs can strain budgets and affect the project viability. Therefore, it is essential for all the stakeholders involved to understand this risk profile or risk envelope, to plan realistically and to manage expectation appropriately. Risk profile improvements. So what do we have to do? Well, as shown in this figure, we want to change this risk envelope from scenario 1 to scenario 2, where potential risk envelope is smaller. So to achieve this, in addition to minimizing the unknown and uncertainties, it is very important, or it is necessary, to reduce the performance risk of the remediations. To reduce the performance risk, it is important to conduct preparatory work, things like pilot test, tracer test, treatability studies, bench scan, so and so. So those preparatory works to determine the feasibility of the selected remediation options before designing and implementing at the sites. And then outcome of this preparatory work should inform to the remediation design in order to develop a tailor-made remediation system for a site. So by optimizing, designing, adapting site-specific information, applying target remediation options can reduce performance risk and will accelerate the progress. So this not only reduces the overall cost, but also shorten the project timeline, minimizing potentially long-term liabilities and stakeholder risk, while increasing confidence in successful site closure. Groundwater remediation linkages. Just to give you an idea, this figure shows the possible contaminant linkages associated with the NAPL and the groundwater. There may be more others. However, in general, these are the common linkages which we are trying to address or manage during groundwater remediations. Now, the groundwater remediation linkages could be leaching from soil and entry into groundwater, migration of dissolved phase contaminants into wide aquifer, or to receptor like abstraction well, surface water, or sensitive site. Or linkage could be a migration of vapor originated from groundwater and indoor inhalations. And these are the sort of common contaminant linkages associated with the groundwater. And then if we have the NAPL beneath the site, the problem becomes a little bit more complex because NAPL is acting like a secondary source, whilst partitioning into dissolved phase, gaseous phase, and also absorbing into the soil. So it will create a multi-phase system with complex contaminant fate and transport mechanisms, making the remediation is a little bit more difficult. The groundwater remediation objectives, simply the ultimate aim is to break the complete contaminant linkage. The remediation objective should be site-specific and focus on reducing, controlling, or removing risk associated with the contaminant, complete contaminant linkages. Typical objectives include to remove the source, decrease contamination, contaminant mass or concentration or mobility or toxicity, and then break contaminant pathways, effectively contain the contaminants, and then protect or manage the receptor. It is also necessary to develop remediation criteria remediation criteria are site-specific measures against which you will assess compliance with the remediation objectives. They are usually quantitative and support the regulatory decisions as well. Therefore, the data should be collected during both the operation and validation stage to demonstrate that remediation objectives are met at a site. And also, it is important to back up your conclusion with the site-specific data. So you should collect multiple lines of evidence to demonstrate the meeting of remediation objectives successfully at the sites. So let's have a quick look at about some of the groundwater remediation technologies. And this is a list of common remediation technologies. There may be more others. However, in general, these are the common remediation technologies you can come across during groundwater remediations. Now here, I have tried to group them based on the contaminant mass removal mechanisms. However, there may be some overlap if you look at some of the technologies. Physical remediation technologies such as total fluid pumping, dual phase extraction, vacuum enhanced recovery, multi-phase extraction. So this technology uses a mechanical or physical process to remove, separate, contain contamination in groundwater, potentially without changing its chemical structure. Now, chemical remediation technologies like chemical oxidation, in situ chemical reduction, involve chemical reactions that transform or neutralize or stabilize contaminant in groundwater. Then biological remediation technologies like biostimulation, augmentation, engineered anaerobic bioxidation, NCD, MNA, sparging, phytoremediation. So technologies like this use microorganisms, plants, or enzymes to degrade, transform, or immobilize contaminants naturally or through engineered enhancements. So, and then finally, thermal remediation technologies like steam injection or enhanced electroresistant heating, apply heat to the surface, subsurface to increase volatilization, enhance degradation, or destroy contaminants directly. So these are sort of like a common sort of like a remediation technologies used for groundwater remediation. So during the decision-making process, you will identify one of these as remediation options for your site, or you may have use these technologies in a series, multiple of these technologies in a series. Now that sort of situation we call it's like a treatment train approach. So there you use several different technologies to enhance the performance of your remediations. So I'll show you very quickly a case study. This is a confidential site. The site was decommissioned to be developed as a high-density residential end use. After a series of site investigation, we completed the detailed quantitative risk assessment, and the outcome of the detailed quantitative risk assessment identified two potentially completed contaminant linkages. The first one is a migration of vapor originated from the dissolved phase contamination into air space, followed by the inhalation. And the second one is the offsite migration of dissolved phase contamination into the wider aquifer and to a nearby river. So during the decision-making process, we completed a screening of feasible remediation options and detailed evaluation, followed by the sustainability assessment. And the outcome of this assessment identified sparging and soil vapor extraction as the most technically effective and sustainable remediation option for this sites. So then we completed a pilot test to determine the feasibility of the selected options, and then to collect the site-specific information to inform the remediation design. A tailor-made remediation system was designed, implemented, and operated for about 15 months. Now, this graph here shows the cumulative contaminant mass removal. The curve has been reached and also the measured PID readings readings and collected during the remediation system. So this now, and then we collected the groundwater samples also to assess the groundwater quality. The groundwater concentration also went down quite significantly, and the chart here shows the significant reduction of benzene in groundwater by the end of the remediation. Now, overall, we have achieved more than 90% reduction in the dissolved phase concentration, and we met our remediation target at our sites. So, as you can see, we have followed the process I described before. We did enough investigation to develop an appropriate conceptual site model, and then to identify the complete contamination linkages with the site. Then through the decision-making process, we selected the technically effective and sustainable remediation options for our site, and then did the pilot test to assess the feasibility and to collect the data to support the remediation designs. We operated a tailor-made remediation system with the necessary adjustment to maximize the effectiveness of the remediation system and to collect the multiple line of evidence and demonstrate the remediation objectives have been met successfully at our sites. So using this data and a line of evidence, we got the sign off from the regulator. So probably this is how we have to do remediation at our sites effectively and successfully. So as a summary, when you come to the groundwater remediation, do the sort of like develop an appropriate CSM and then follow the decision-making process to select remediation options, and then conduct preparatory work to minimize the performance risks, and then finally operate an effective remediation system and validate with the multiple line of evidence the success of the remediation. And then one important thing you have to remember is the success of groundwater remediation depends on more than just applying a technology at the sites. So probably that's all I have to say today, and thank you very much for listening, and happy to take a question if there's any.
Brilliant. Thank you, Anil, for that presentation. So me and Anil, cameras back on. So we've got a number of questions that are coming through the portal. So again, thank you for that really good presentation and a really clear example there, case study. So first question, how do you balance sustainability with achieving the risk reduction targets?
Okay. Well, like I said, the sustainability cannot override or compromise the risk assessment work. The risk mitigation work. So sustainability should complement, not compromise, the risk reduction process. So if you have a problem or identify risks at our site, we do have to do the mitigation work. However, when you are doing your selections and sort of like finding the right remediation options, then you have to consider all the environment, economic, and social aspect of your projects to identify most sustainable options for your site. So basically, you have to mitigate your risk considering the sustainability and sort of like using the most sort of like a sustainable remediation option for your site. Now that's why I said, like in my presentation, like when you are doing sustainability assessment, you have to consider probably like a top 3, 4, 5 remediation options selected from the detailed evaluation, because from the outcome of the detailed evaluation, the technology is more like the top few technologies should be more likely to be most technically effective. Therefore, we use technically effective remediation options to do the sustainability assessment. Therefore, we can sort of identify most sustainable, most technical remediation options for your site. So yeah, so then that's how I think we have to sort of like incorporate sustainability into our sites. And and also like during the practice, you can consider about the sustainable management practice also. So that will sort of like a potentially further enhance or further increase the sustainability at your projects. And yeah, so basically, like I think if you look at the ISO 18504, so that sort of like that guidance emphasize it says that the sustainability cannot override or dilute the need to manage the risk, and it must work alongside it to deliver safe, efficient, and responsible remediation. And so I think that's how it should be done. Yeah.
Right. Okay. Thank you for that. We've got one here. In areas with blowing sand, so I think, is there particular ground conditions that could limit the certain remediation techniques? So the question mentions blowing sand, but is there particular ground conditions that can impact on the remediation techniques used?
Sorry, can you say it again? Here, I didn't hear the question.
So the question was, in areas with blowing sand, have you found this to limit the use of certain remediation techniques? But on a wider thing, is there particular ground conditions that limit then what remediation we can use?
Yes, I mean, like the remediation techniques is site specific. So you have to, like I said, that's why we have to collect all the geology, hydrogeology, and all the information before we do the remediation. So basically, the remediation technologies depend on the site-specific conditions like geology. If you have the permeable geologies, you can sort of like do like a simple like a groundwater pumping, soil extraction, aspargine, that kind of things. But if you have like a low permeable soils, the geology, then probably you can do the sort of like a vacuum enhanced recovery kind of technology. And also, if you look at the thermal remediations, the low to moderate permeable soil is much more effective with the thermal treatment. So it's, yes, it will depend the site geology or site material, the geology or the permeability will have a bigger play when you are selecting the remediation options for your site.
Right. Okay. So a follow up to that, someone's asked, with the thermal treatment, is there an ideal ground conditions, and is there a risk of impacting soils such as within chalk soils?
Well, yes. Thermal treatment, as I said, is mostly effective with the low to moderate permeable sort of soil, such as maybe like a clay and silt. The problem is, like, if you have like a high permeable soil, then the water coming influx of the water is quite high. Therefore, we probably struggling to get the right temperature, the required temperature, or we may have to sort of like increase the number of heaters installed. So like it will be dense heaters, and then it will require higher energy requirements. So because of that, if you have like a high permeable sort of like a geology, then it will have a little bit challenge to find the right balance to reach the effective temperature. And also it may require like, as I said, like the requirement of the energy may be quite high. So when it's come to the chalk, if you have like a fractures, quite like a multiple fractures, and it's like a very dense fracture system, then you have like quite a lot of high permeable system, system. Therefore, reaching to the right technology and right temperature would be challenging. So it's a little bit like balance. You have to find whether that technology, whether applying the thermal in the choke is feasible or not. However, if you look at the literature, thermal has been applied in the choke aquifer, so it is possible. However, you need to find the right balance, considering all the cost and all the other requirements to identify whether it's the most appropriate technology for the job.
Right. Okay. So, question here: what physical barriers can be used within the ground to control groundwater?
Right. So, as barriers in the ground, we can use like slurry walls, or we can use sheet piles. In addition to probably we can use this sort of like a diaphragm or cutoff wall or secant wall. So those things sort of like sort of potentially will stop water coming in. However, the important thing is like you have to, when you are sort of like thinking about the physical barriers, you have to consider your site-specific conditions, and probably these kind of things will be applicable if you have like a thin aquifer, where then you can sort of like anchor these walls or barrier into the sort of like aquitard or low permeable layer. So then you probably have a complete cutoff or protect your receptor. Otherwise, there may be a potential water to go underneath these things. Like if you install them as like a hanging barrier, it may not be fully. You may not be able to fully protect your receptor. So it has to be site specific again, and you have to think about site conditions before you select those things as options.
Okay, I think one final question, if that's okay. Have you undertaken remediation where the groundwater was under artesian pressure? And do these artesian pressures then affect what remediation techniques can be used?
Not personally, but it may apply because of change. But then, like if you can sort of like deliver something like use potentially like a thermal technologies, and also like a reagent injections for either chemical or biological process, you should be able to manage and remediate those kind of scenarios.
So you then be having to deal with the under pressure then, rather than yeah, it's interesting challenge, that one, isn't it?
Yeah, it is. Yeah.
Yes. Right. Okay. We'll end the questions there, and further questions will be answered by Anil once he's had a chance to review these. So again, a big thank you to Anil for the presentation and for the answering the questions. Our next Down to Earth talk will be on Tuesday, the 11th of November, and we'll be looking at geophysical assessment of infrastructure and looking at the investigation of rail and highway environment. Please remember to complete the feedback following the presentation, and thank you for attending today, and we'll see you again in November. Thank you very much.
Thank you.